we are going to discuss about in detail how those control logic design can be done. In the previous video, I explained the 4 different methods by which you can design a control logic. The first method was a one flip-flop per state method. Okay, so that was also called as a hardwired control method. So we are going to see with an example how this one flip-flop per state method can be used in designing a control logic circuit. Okay, so 3 questions can actually come from this particular section for your university exam. Either the question could be with an example, explain how a hardwired control mechanism can be used for designing a control logic, or it can be either using a one flip-flop per state method, how you can design a control logic circuit, or either it could be in this form also, perform a control logic design or design a control logic circuit for signed magnitude addition or subtraction. So actually 3 type of questions can be answered from this particular section. So let's move on to this method. So every design will have a set of steps for designing that control logic. So as in that, our one flip-flop per state method is also having 5 consecutive steps to design this control logic circuit. The reason why this is called as a hardwired control method is because it has a lot of circuits. Each of them is connected with the wires, and for any modification or any change in the circuit, you have to remove that circuit, you have to then insert the logic and then again rearrange the wiring. So that is why it is called as a hardwired control. Okay, so coming back to the steps, the first step is stating the problem. What exactly is our problem? Then based upon that problem, you will come up with an initial equipment configuration that is required, or you are assuming a initial equipment configuration. Then you will formulate an algorithm. Then the data processor part is specified, and finally the control logic is designed. So in 5 steps you are going to design a control logic using the one flip-flop per state method. Now moving on to the first step, that is stating the problem. What is the problem exactly here? We are going to implement a system, or we are going to design a control logic circuit that can perform signed bit number addition and subtraction. That is, it should perform addition of 2 numbers or subtraction of 2 numbers, but these numbers will definitely have some sign. Okay, so that is the problem. And also the result which we obtain, definitely that will also have a sign magnitude. And also we know that when you perform addition of 2 numbers, there is a possibility that a carry can come. Okay, so if a carry can arise, then that carry need to be stored somewhere. The normal registers will not have space to store that carry, so that is an overflow that has been generated. So that overflow need to be stored in some other flip-flop, or it should be stored in some other register. So these are the problems we address in this particular problem. It is the addition of 2 signed numbers or subtraction of 2 numbers, and the resultant will also have some sign. And also if a carry is being generated, or if an overflow is generated, it should also be stored somewhere. So these many problems need to be addressed while designing. So if our n bit number is represented in this form, n-1 bits will represent the magnitude, and the most significant bit will be representing the sign, or you represent it as S. Okay, now moving on to the next step. Step 2 is equipment configuration. You are going to assume the equipments that are required. We know that it is 2 numbers that is going to be added or subtracted, so definitely you require 2 registers to store those numbers. Since it is an addition or subtraction that need to be performed, you require an ALU, or an arithmetic logical unit. And to decide between whether it is a subtraction or addition, you need a control logic to select that. And then you require an overflow flag, overflow register to store if any overflows are there, right? So this is the equipment configuration that is required. The magnitude of register, magnitude of number B is stored in register B. Magnitude of number A is stored in A register. BS represents the sign of that B number. AS represent that bit to store the sign of the number stored in A register. If both of them, if they are performing an addition and if it generates a carry, that carry or overflow should be present in this particular E register. And this control logic has two inputs and one output. The input is QA and QS. If QA is set to 1, it means that it is the addition that need to be performed by the ALU. If QS is set to 1, it means subtraction need to be selected by the ALU. And if X is indicating whether that operation is terminated or not. So if X is set to 1, it means that the current operation is terminated and the system is ready to take up the next operation. So this is the equipment configuration that has been done in the step 2. Now the next step is you have to come up with an algorithm to solve this particular problem. So what is the algorithm requirement? Let's see. We know that addition and subtraction, those are the two things that need to be done. So subtraction we are going to rewrite in this form. A minus B can be written as A plus minus of B. We know that this can be rewritten in this format. Using the same principle in our algorithm, we are going to come up with another 4 cases, that is subtraction of two positive numbers. You can rewrite it as plus A plus minus of B. This is the same as A minus B, right? So similarly, subtraction of positive A and negative B can be written as A plus B, right? You're taking the minus inside. This can be rewritten in this format. So what you're going to do actually in this case is that all the cases of subtraction you are actually converting in the form of addition. Okay, that is all subtractions you are changing it into the form of an addition format. That is what it has been done. Now for subtracting A and B, where A is a negative number, you can rewrite in this form minus A plus of minus B. And similarly, subtraction of two negative numbers can be written as minus A plus B. Excuse me. Now the next thing which you are going to do is, when numbers are added or subtracted, algebraically we find that there are 8 different conditions to consider. So those 8 different conditions, depending upon whether A is greater or A is smaller than B, you rewrite those all conditions here. So this is nothing but all these 4 things which we have written here. You are writing it down and you are telling up the different 8 possibilities if A is greater than B. So let's take the first consideration, that is when A plus minus B. Okay, so the first case here taking is both A and B are positive. So this case, second case here, A plus of B. If A is greater than or equal to B, then you can rewrite it as, you can just do A plus B and give a positive sign for that. Okay. Now if in case A is less than B also, you can do the same. You can do A plus B and give a positive sign. Now for the operation A plus minus B, and if A is greater than B, then what you should do? You should do a subtraction of A minus B. That is, B should be subtracted from A and a positive sign should be given because A is having a greater value, because A is positive, right? So the positive, the highest numbers signature will be given in the resultant magnitude, the basic principles which we have studied in maths. Similarly, if A is less than B, then the answer will be negative, because here B is negative, so definitely the result will also be negative because here B is greater. Then you perform B minus A. So likewise, you are rearranging all the different 8 possibilities that can come up with a subtraction of numbers, 2 numbers in which either one of them could be negative. So what you're doing in this algorithm design is that you are basically rewriting all the subtractions in terms of addition, which is much easier. We know that to perform subtraction, it is just the addition of a 2's complement of that particular number. So you need to do that particular operation. For that, you are rewriting it. So this is the 8 different possibilities. Now for simplicity, I've actually explained the entire thing using an example. Remember that for your exam purpose, it is not necessary that you have to write this example and explain it. This is just for your understanding purpose. So let's see one by one how these conditions are being done so that you will get a better clear idea. Let's take the first condition where A is greater than B and you are going to perform an addition of a positive A and a negative B. Okay, if this is the condition which you are going to consider. So here you are going to give an example number for A and B. So for A I am giving the magnitude 4 and for B I am giving 3. So basically what you're going to do is 4 minus 3. Decimal number 4 and decimal number 3, you're going to subtract it and just see whether you're getting the correct result. You should get 4 minus 3 if you're doing it, and if A is greater than B, then definitely you should get a positive 1. So you're just checking whether you're getting positive 1 if you're doing with this algorithm. Okay, so according to our rewritten steps, A plus minus of B is nothing but A plus 2's complement of B, right? Minus B can be written as 2's complement of B. So B here is 0, 1, 1, that is 3. So 0, 1, 1, when you take the 2's complement, it is 1, 0, 1. Okay, so 0, 1, 1's 2's complement is 1, 0, 1. You are adding A and 101, you get 001. That is, you have a carry 1. This carry is now represented in the overflow and the result magnitude is 001. 001, which is nothing but the decimal number 1. And the result sign is positive. Definitely, since A is positive, the result sign will also be positive. So what you understood? The first result carried out was correct according to our algorithm. Now similarly, we are going to see one more example for that. In that case, A is greater than B and A is given a negative value, that is minus A plus B. In that case, we can rewrite it as, definitely by taking the signature minus outside, you can write it as A minus B, and A minus B is nothing but A plus 2's complement of B, right? So A plus 2's complement of B, just like in the previous case, you're doing it again, you got 001 and with 1. Here you have a negative sign because A is the greatest number and the sign of A is negative. So that is why in the result also you have a negative. But the answer is again 4 minus 4 plus 3, which is minus 1. So that is again the result magnitude is 001 with the result sign minus. Okay, understood? So these two cases we have seen. Now there is another case that comes when you don't have a carry flag. When you have a carry flag or when you have an overflow, result is directly been written as such, 001, you get the result as such. Now in this third case, just listen here. In this third case, what you're going to do is you are doing subtraction in which positive A and negative B, you can rewrite it as A plus minus of B. You can write it as minus B minus A. It is nothing but A plus minus B. And then this again can be written as B minus A. So you're subtracting A from B, so which you can also be rewritten as A plus 2's complement of B, right? So you can write it in this form also. So now you're doing A plus 2's complement of B. 2's complement of B, when you do it is 100. So here in this third case, B's magnitude is 4. Okay, so B's magnitude is 4. So 100's 2's complement is 100 itself. So that is why it is 100 here. Okay, so here in these two cases B's magnitude was 3, but in this third case we are taking B's magnitude as 4. Okay, so this is the highest value. B is having a highest value here. So A is smaller than B. So here again 2's complement of B is 100 itself. When you perform the addition, you are not getting a carry. So when you're not getting a carry, what do you do? When you're not getting a carry, what should be the actual answer? The actual answer should be 3 minus 4. What you should get minus 1, right? But what is the answer you get here? You get it as minus 7. So that is a wrong answer. So to get the correct answer in the cases where carry is not generated or when no overflow is there, you have to take the 2's complement of the result. Remember, when carry is not there, you have to take the 2's complement of the result. So 2's complement of 1 1 1 is 0 0 1, which is the correct answer. That is 3 minus 4 will give you minus 1. You already have minus from the sign itself, and you got the answer here. Similarly, one more case I'll explain. Here also B is higher, B is having a greater value, so B's magnitude is here 4 and A is 3, and then you perform minus A plus B, which can be written as B minus A, which is nothing but A plus 2's complement B. You do the same operation as the previous one. Here also there is no carry or overflow. So in order to get the correct answer, you should take the 2's complement of this particular result. I have not written 2's complement here, so just remember this 111's 2's complement is taken to get the result 001. Okay, so you get the 001 here. Positive B, and B is higher, so the magnitude or the result sign will also be positive. Similarly is the other two cases, which you will understand. So once again I'll explain, this example is not actually required in your exam. This is for your understanding purpose, and this will give you a better idea when you design the flow chart in the next step. Okay, so here you came up with an algorithm, and with that algorithm you're going to design a flow chart for this sign, magnitude, addition and subtraction. So how is this flow chart? So initially, for the operation to start, your x should be equal to 1, and then from that state, in order to go to the next state, that is whether to perform an addition or whether to perform a subtraction, depends upon the symbol QS. If QS is equal to 1, then it means that it is a subtraction that is going to take place. If QA is equal to 1, then it means that it is the addition that is going to take place. So what is the next thing that has been done in the QS? If it is 1, if QS, if it is 1, it means that it is a subtraction. So the sign magnitude, that is the sign of that particular B register, is being complemented. Let's see how it is being done. See here, in all the subtraction cases, whatever was the sign bit of the B, you are complementing it. Plus B is converted to minus B, minus is converted to plus, plus is converted to minus, minus is converted to plus. So that is represented in our flow chart. That is represented in our flow chart. So whenever it is a subtraction, the first thing you do is converting the sign of that BS to complementing the BS signature and storing into BS. So whatever is the sign, you take the complement of it and store it into the BS register. If it is addition, you can directly go and check whether the sign bit of both AS and BS are same. If both are same, then what do? If both are same, you perform just the addition of A plus B, store it in the register A. If any carry is there, you store it into E, and then you go back to the initial state. So if both A and B sign bits are same, that is if it is minus for both A and B, or if it is plus for both A and B, you just perform the addition, and if any carry generated, you store it into the register E and go back to the initial state. Now the real thing that need to be done is, if both of them are not the same, signs are different, then you have to perform the 2's complement of B, right? You are adding the content of register A with the 2's complement of the content of register B, and if any carry is there, you store it into E register. Now is that all enough? No. Again, to get the correct result, if carry is set, that is E is equal to 1, if carry flag is set to 1, then you can reset that carry flag and go back to the initial state, because you have received the result correct. Now if carry is not set or overflow is not set, as in that last cases which I explained, in these two cases, if the carry is not set, then what you have to do, you have to take the 2's complement of the result, right? So now the result is stored in the register A. So that is being done here. A is being complemented and stored in A, and then the content of A is added with 1. So this is nothing but these two steps denote the 2's complement of the resultant that has been performed, because the current result is now in A register. A plus B complement plus 1 has been stored in A register. So the result is in A. The result is being complemented if no carry flag or no overflow is being set. Okay, so now you understood how you came up with this flowchart or algorithm based upon that particular example. Okay, so like now we understood that our example of flowchart is giving you the correct result. So based on that, we will design the data processor register and ALU. So this is BS and AS for storing the sign bit of B register and A register. So two control lines are being given to AS and BS, that is Y and Z. Now whatever is being performed in the ALU, we have studied in the design of the ALU in the 5th module that there are 4 control lines required to select the mode, select the operation, etc. So S2 is going to select the mode, whether it is an arithmetic operation or whether it is a logical operation. S1 and S0 and CIN together will select the operation, whether it is an addition, subtraction, or whether it is a complement or transfer or whatever it is. Okay, so from B register and A register, contents are given to the ALU. Addition and subtraction is performed here. If a carry is there, that carry is being transferred to E register. And there is another control line W that is used to set and clear this one. E. Similarly, Z and Y control lines are used to clear and set BS and AS respectively. Okay, so that I'll explain it later. And L here is another control line that is used to set or reset the A register. Okay, so understood with the step of designing the flow chart or designing the algorithm. Based upon that algorithm, you designed the control logic, and then you're going to design a system block diagram. So now you have the control logic. We know the inputs that are being given to the control logic is QA, QS, AS, BS and E. That is QA to select an addition, QS to select a subtraction, AS and BS are the 2 registers, that is the 2 operands, E is the overflow bit. Okay, so AS and BS are given in an XOR. That means that if both the signs are same, okay, if the signs are same, then it is equal to 0. An XOR operation is equal to 1 if 2 signs are not the same. So if both AS and BS are not having the same sign, then there is a 1 that is given as the output here. Otherwise a 0 is given as the output. And these many control lines are being received from this control logic. Okay, so we'll see which all are these things and what are the functions of this. X is used to denote the initial state. So when X is set to 1, it means that it is ready to take up the next operation. The current operation is terminated. This is mode select for logical operations or for arithmetic operations. This is for function select, input carry. L is for loading into the accumulator and the E register. Y is for complementing the BS, Z is for complementing the AS and W is for clearing the E. So these are the different control lines that are present in the control logic. Okay. Now next we are going to design the state diagram. So the step 4 is to design the state diagram. We know what a state diagram is. That is a transition diagram from one particular state to next state. How is that transitions being done? So all these circled states are basically different transitions. T0 is the initial state. From T0 to T1 is the first transition. And remember that all these transitions happen in one clock cycle. That is, T0 happens in one clock cycle, T1 happens in another clock cycle, T2 in another clock cycle likewise. And the conditions that are required to move from T0 to T1 is being represented in this directed lines between these functions. Okay, so these are the different micro operations that must be executed at a given state within a function box. So how do you come up with this state diagram? It is simple. You can directly draw it from the algorithm or the flow chart which we have designed in the previous step. So I have just written down that particular flow chart. So it is the same flowchart which we saw earlier. So from that flowchart we are going to draw the state diagram. So initial state is nothing but T0. So in that T0, which all are the control lines that helps in remaining in T0? QS if it is 0 and QA if it is 0, then you remain in that state T0. To move from T0 to either T1 or to move from T0 to T2, you require these control lines to be set to 1 respectively. Okay, so QS if it is set to 1, it means that subtraction. Subtraction means you are complementing the sign bit of B register. So this is the T1 state, and if it is QA is equal to 1, QA if it is equal to 1, you directly come to check if whether the sign bit of AS and BS are equal to equal. So this is T2. So this is T1, this is T2. Once you are in T2, if both the signs are equal, then you can just perform the addition, copy the carry or overflow to E and go back to the initial state. So this T3 represents this one. So from T3 you can go back to T0 without any conditions. Without any conditions you can go back to T0. Okay. Now if S is equal to 1, that is S is equal to 1 means that the signs are unlike. The signs are not equal. If signs are not equal, then you have to come up to do with the subtraction by using A plus 2's complement of B. So here in T4 is shown here. T4 you are doing that particular step. After T4, now you come up with the next step of comparing the control flow. Control flow if E is equal to 0 or equal to 1. If equal to 1 means that you have received the result as such, you can go to the initial state. See, if E is equal to 1, then you just reset the flag and then reset the overflow flag and then go back to the initial state. So here in this particular T5, you are checking this condition, and if T5 after T5, if that condition E is equal to 1 is satisfied, you can directly go back to the initial state and take up the next operation. If it is equal to 0, then you have to do two things. What all are the two things you have to do? You have to take the complement of the result set and then add 1 to it. That is, you are taking the 2's complement of the result set. So this T6 is taking the complement, and T7 you are taking the you are adding 1 to that complement, and then also you are taking the complement of sign bit of A register. That is also been performed in T7. After T7 you can go to the initial state. So this is how from this particular flowchart you come up with this state diagram. Okay. So once that is also done, the next step is you are going to write down a sequence of the register transfers. Okay, so we'll see what all other register transfers that are being performed here. Okay, so the first register transfer in the first state, what it is done is initial state. In the initial state, only X is equal to 1. That is, it is ready to take up an operation. Okay, so in that state, all other lines are 0, only X is equal to 1. Now from initial state T0 to next state T1. Okay, in next state T1, what is happening in T1? You are complementing the sign bit, right? To complement the sign bit, what do we have to do? To complement the sign bit, here Y is the control line that is used to complement the sign bit. So here respectively you are going to set Y as 1, all other lines remains 0. Okay. Now in T2, what is happening? T2 is nothing, right? T2 you are just doing a comparison operation of both the sign bits. So you don't have to check any control lines. So all the control lines remain 0. In T3, what you are going to do? T3 is nothing if it is a normal addition that is being done. Okay. So in this normal addition, it is content of register A and content of register B is added and stored into the register A, and if a carry is there, that carry is moved to E. Now for that particular thing to happen, you have to refer our function table of ALU. Remember this function table of ALU which we studied in the 5th module. This is the diagram this is the table which we studied for designing of the ALU. I hope you have studied that during that particular time. So here just check what A plus B is doing. For A plus B, or for addition to happen, the flags that need to be set, or the bits that need to be set is S2 remains 0, S1 remains 0, S0 should be 1 and Cin should be 0. So similarly S0 should be 1, because here also S0 should be 1. So S0 is set to 1, and the reason why L is set to 1 here is for this reason. Whatever carry, if it is there, you are now going to load it to the E. So for loading it to E, loading A or E from ALU, you have to set this L bit. Okay, so that is the reason why here L is also set to 1. So S0 is set to 1 because we are doing an addition operation. From the function table of ALU, we understood that S0 should be 1, then only you can perform an addition operation here. And L is set to 1 because you want to set the E flag. Let's take the next one. In T4, what is happening? In T4 state, what was happening? This was the function that was happening. That is subtraction. A plus 2's complement of B is being added. So this is nothing but subtraction that is being happening here. So what do you do for subtraction? In subtraction, from the function table of ALU, to perform an A minus B, S1 should be set and Ci in should also be set. So S1 should be set, Ci in should also be set. Here also whatever the carry is being generated is loaded into the E register, so that L flag should also be set. So that is the reason why S1 is set, Cin is set and L is set. Now in the next case, what has been done? In the next T5, what has been done is you are checking whether that particular E is equal to 0 or 1. Okay, so E is equal to 0 or 1, just require one condition to be set. For clearing that E, you set W is equal to 1. So what is happening here? So if in T5, what happens is in T5, this E is set to 1. That is, if E is equal to 1, then you are going to clear that particular carry flag and go back to the initial state. Okay, that is when, because you have received the result here in this condition. After this particular 2's complement thing is being done, if a carry is there, then the result is directly present in the A register. So you don't need this E register anymore. So you are resetting it. So in T5, you are actually resetting it. So resetting and going back to the initial state. So for resetting it, which is the control line used, W is the control line that is used to reset the E. So that is the reason why in this particular T5 only W is set and all other remains 0. Now in T6, what has been done? You take a complement of the content of the result set, or the complement of the content of the register A. To take the complement of A, what is the function that is being done here? Let's check. See, for complement of A, you have to set S2, S1 and S0 to 1. So you set S2, S1 and S0 to 1, and L is also loaded with 1. L is also loaded with 1 for the reason that loading accumulator and E from ALU, you require L to be set to 1. So after complementing, you need to load it back to A, right? So that is the reason why L is set to 1. Now the last state, that is T7. In T7, what you have done, you are actually adding 1 to the content of the result set to make it the 2's complement of the result. So A plus 1. So incrementing A is being happening here in T7. Incrementing A requires only Cin to be 1. So Cin is set to 1 and L is set to 1 because you are loading it to A. So load need to be set to 1 and Z is set to 1. The reason why Z is set to 1 is, let's see, Z flag is the complement of AS. Okay, so here we know that AS is complemented and stored into AS bit. So that is the reason why Z flag is set to 1. So now you understood how the sequence of the register transfer is being denoted in this table. It is by looking into the function table of ALU. So it is necessary that you study the function table of ALU by heart. Only if you study this function table of ALU you will be able to design. So you don't actually have to study by heart the sequence register. It is the function table you have to study. Based upon the function table you are filling the values for all these. Okay. Now for the last step, it is the design of the hardwired control. So you are ready with the algorithm, you are ready with the table. Now you are going to design that hardware part. So to design that hardware part, we know that this is a one flip-flop per state method. That is, each state will have one flip-flop. So how many states did we have? We had a total of 8 states, right? From the transition diagram or the state diagram, from T0 to T7 you have 8 different states. So for 8 different states, one flip-flop each. So total of 8 flip-flops you require. And which flip-flop you are going to use here? It is a D flip-flop which you are going to use here. Okay, we use a control organization that make use of one flip-flop and choosing a D flip-flop. How does a D flip-flop work? The next state of a D flip-flop is a function of that input and it is independent of the present state. So it doesn't depend upon the present state. It is only depending upon the input that is given to the D flip-flop. Okay, so based upon that you are going to use the different flip-flops. So DT0 means the flip-flop that is present in the T0 state. T1 state, flip-flop present in T2 state, flip-flop present in T3, likewise. Now how do we come up with this equation? Okay, to come up with this equation, let's see how DT0 or T0 can be reached. Okay, so let's go back to that state diagram. To reach T0 or to remain in T0, what you have to do is QS should be set to 0, QA should be 0, or you can come from T7 to T0 without any input. You can come from T5 to T0 with E is set to 1. You can come from T3 to T0 without any input. So these are the different possibilities to reach T0. So that is what is written here. QA and QS is complemented because both of them need to be 0 to remain in T0. You can come from T3 directly. You can come from T7 directly. From T5 you can come only if E is set to 1. So once again I'll explain. From T3 you can directly come. From T7 you can directly come. From T5 you can come to T0 only if E is set. From T0 to remain in T0 you need both of them to be cleared. So that is the reason why you came up with this particular equation in DT0. In DT1, how do you come to DT1? From DT0 you can come to DT1 only if the QS flag, if the QS is being set. See, from T0 to T1 you can come only if QS is set. So that is the only possibility to reach that state. Now the next one, T2. How you can come to T2? You can come to T2 from T1 and also from T0. Let's see how that. From T2 you can come from T1 without any input. You can also come from T0 with QA set. So that is how it is shown here. QA can be set and you can come from T0. From T1 also you can come without any input. Similarly, to reach T3 you need to have S bit cleared, and also you can come only from T2. From T2 you can come to only from T2 you can come to T3 only if S bit is cleared. You can come from T2 to T4 only if S bit is set. See, S bit is set, S bit is cleared. You can reach T3 when S is cleared. You can reach T4 from T2 only if S is set. So similarly you write down all these things. Okay, and now what is the Boolean function for the output control? So you have to write down the different Boolean controls for the different output control. How you can write that is, just look at X, which all conditions or in which all states X is set. Just see that X is set only in T0 state. So that is why X is being controlled by this particular state. Now S2 is being set only in the state T6. So T6 is the only state in which S2 can be set, or it controls. T6 is being S2 can be controlled by this particular state T6. Now S1, T4 and T6. S1 is set in T4 and S1 is set in T6. Similarly, L, T3, T4, T6 and T7. L is set in T3, T4, T6 and T7. Similarly, W is set in T5. W is set only in T5. So this part of that table represent the Boolean functions that are required to control that output. Okay, and this is the flip-flop design, of how that particular flip-flops need to be designed in order to do this one flip-flop per state method. So you require 8 flip-flops and the flip-flops need to be arranged in this particular hardwired unit. This is the logical relationship between how these flip-flops should be there, or how these flip-flops should be arranged using a hardwired mechanism.